Hello friends, welcome to UGC EPG Pathshala. I am Dr. Satya from the discipline of Geography, School of Sciences, Indira Gandhi National Open University, Delhi. Today I am going to elaborate upon progress in climatology, satellite climatology and GIS, which comes under the paper Climatology. First of all, let us discuss what could be the possible learning outcomes of this module. While going through this module, you should be able to define satellite climatology and GIS, explain about technological progress in climatology, state the basics of satellite remote sensing, distinguish between geosynchronous and sun-synchronous orbits, describe the importance of satellite climatology for weather forecasting, and summarize the final representation of climatological data on a GIS platform and its applications in various fields. In this course so far, you have learnt about the history of climatology and general conditions of the atmosphere and its circulation. You have also learnt about the phenomena that leads to various weather events, which might be even the extreme ones like floods, cyclones, thunderstorms, etc. You may also recall climatic classifications given by scholars like Koppen and Thornthwaite. In this module, you will learn about the progress in the field of climatology with special reference to satellite remote sensing. You will also get acquainted with the process related to collection, storage, manipulation, analysis and retrieval of weather related data with the help of Geographical Information System or GIS, which involves the use of hardware, software, trained professionals, etc. to handle such enormous amount of data. Technological progress in climatology. Today, technological progress in climatology is attributed to the use of remote sensing and GIS in climatology and meteorology. They have revolutionized the studies in climatology and deals with variables which are spatial in nature. Both technologies, that is remote sensing and GIS, are correlated, as remote sensing helps us to sense the area of interest from a distant place, while GIS helps in the storage, analysis and final display of the required data. The progresses can be grouped into different stages. In very brief, they are the infantile stage. Prior to the advent of satellite data and GIS technology, most of the climatic data was collected with the help of ground survey. Weather forecasting must have been done in the primitive times too, with the help of certain basic observations like wind direction, cloud cover, sky color, position of planets and satellites, etc. However, systematic weather forecasting is being done since 100 to 125 years. Now, the beginning of takeoff stage. Dissemination of weather related information was facilitated with the advent of telegraph in the year 1840. It helped in the collection and propagation of weather data and reports to each and every part of the world. Systematic collection and dissemination of weather related information with the help of telegraph took 2 more decades and was started in England in 1860. Pioneers among the weather telegraphy were Robert Fitzroy, Urbain Le Verrier of France and Smithsonian Institute located at Washington DC, USA. Among them, Robert Fitzroy was a British meteorologist and captain of HMS Beagle who sailed around the world with Charles Darwin on board as a naturalist. It took another decade for other countries to establish their weather forecasting services. The period 1900 to 1920 marks the second phase of progress in climatic data collection and weather forecasting. This was because of the advent of radio telegraphy. With the help of this, ships and aeroplanes equipped with radio and standard weather instruments could collect weather related data from oceans and upper atmosphere respectively. Now, the takeoff stage. By 1930, it became possible to measure the atmosphere up to 6 to 7 kilometers altitude with the help of aircraft sounding techniques. Still at higher altitudes, techniques like radio and sound wave propagation, observation of auroras, solar particles and cosmic rays were done to collect atmospheric data. The 1940s and 50s marks the application of radar for determining upper winds accurately as well as tracking tropical cyclones, thunderstorms and other extreme weather events. During this period, rockets were also launched which could easily collect information up to 400 kilometers altitude. So, with this, it became easier to explore the upper layers of atmosphere. Now comes the steady state progress. With the advent of satellite climatology, climatic data is obtained through satellites, which covers a wide area that needs to be studied and also provides valuable information related to our atmosphere with utmost ease. Today, satellite climatology has become an important branch of climatology. The first meteorological satellite, TEROS-1, was launched by United States in 1960. The invention of high-speed electronic computers also revolutionized the method of analyzing climatic data. It helped to solve various complex mathematical problems with ease, which is very important in various weather predicting models. Now, first of all, understand the basics of remote sensing in brief in the coming section. Basics of remote sensing. We can define remote sensing as the art as well as science of obtaining information about an object, area or phenomena through an analysis of the data acquired by a device which is not in contact with the object, area or phenomena under investigation. In climatology, the information to be collected includes location and development of weather systems such as clouds, rainstorms, tropical cyclones, cold and warm fronts, etc. For remote sensing, we need a physical carrier which carries information from the object to the sensor. This carrier is the electromagnetic radiation. Electromagnetic radiation is a form of energy that includes radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, gamma rays, etc. It consists of inseparable oscillating electric and magnetic fields that are always mutually perpendicular to each other and perpendicular to the direction of propagation. So, they propagate in the form of wave at the speed of light through vacuum. There are areas of electromagnetic spectrum where atmosphere is transparent, little or no absorption of radiation is there to specific wavelengths. These wavelength bands are known as atmospheric windows since they allow the radiation to easily pass through the atmosphere to the Earth's surface. The atmosphere is practically transparent to visible region of the electromagnetic spectrum and therefore, many of the satellite based remote sensing sensors are designed to collect data in this region. Some of the commonly used atmospheric windows are 0.4 to 0.7 micrometers, that is the visible range, 0.7 to 3 micrometers, that is the near infrared and the middle infrared, and 8 to 14 micrometers, that is the thermal infrared. In the visible and near infrared band, sunlight is predominantly reflected. In the thermal infrared band, the main source of radiation, as the name suggests, is the blackbody thermal mechanism, as every object like water, soil, vegetation, rocks, etc. above absolute zero, that is minus 273 degree centigrade or 0 degree Kelvin, emits electromagnetic radiation. The microwave portion of spectrum consists of longer wavelengths 1 millimeter to 1 meter and can penetrate the clouds, haze, snow, rain, etc. and thus form a valuable region of remote sensing. The data acquisition process in remote sensing comprises of a few elements as it is shown in figure 1. They are the energy source, which is at A, propagation of energy through the atmosphere, which is at B, energy interactions with the Earth's surface features, which is C, airborne space-borne sensors to record the reflected energy, that is D, and the generation of sensor data in the form of pictures or digital information, that is E. Now, the examination of data using various interpretation devices to analyze pictorial data and final compilation of data for various applications. So, we have learned that a satellite sensor not only receives electromagnetic radiation emanating from the object, but also receives the reflected radiation from an external source by the same object. This external source of radiation can be the sun, which is a natural source and accounts for most of the electromagnetic energy recorded by remote sensing systems. The sun can be regarded as a 6000 degree Kelvin black body. The total emitted radiation from a black body is measured in watts per meter square and is proportional to the fourth power of its absolute temperature measured in degree Kelvin. This is known as the Stefan-Boltzmann law and is expressed as m lambda is equals to sigma T to the power 4, where sigma is the Stefan-Boltzmann constant and is 5.6697 multiplied by 10 to the power minus 8 watt meters to the power minus 2 and K to the power 4. So, as the energy is emitted by an object is a function of its temperature, the greater the temperature, the greater is the amount of radiation from the object. Another external source of radiation can be satellite itself, which illuminates up the object to be studied and receives the reflected radiation from the object. This gives rise to active and passive remote sensing. When a satellite sensor generates its own energy to illuminate the surface and records that reflected energy from the target objects, it is called active remote sensing. These radiations operate in microwave region of electromagnetic spectrum and includes wavelengths longer than 1 millimeter. So, active remote sensors are not dependent on the solar energy as the illuminating source. Passive remote sensing basically depends on the solar radiation as the source of illumination. It operates in visible and infrared region of the electromagnetic spectrum. Refer to figure 2 to get a clear understanding of the active and passive remote sensing. Now, let us get acquainted with satellites and different types of weather satellites. Satellite is an object which is put into orbit around the Earth or any other planet in order to relay communication signals or transmit scientific data. Basically, there are two types of weather satellites, namely sun synchronous and geosynchronous satellites. The sun synchronous satellites are much lower in altitude than the geosynchronous satellites. The path followed by a satellite is referred to as its orbit. Now, let us get some more acquaintance about this, the types of satellites. So far, you know that an object in orbit is called a satellite. It can be a natural satellite like Earth's moon or human-made satellite that are employed to collect climatic data or used for communication or navigational purposes. Based on different orbits, altitudes and inclination of the orbital plane with the Earth's equatorial plane, there are basically two types of weather satellites. They are polar satellites, geosynchronous satellites or geostationary satellites. Now, let us know about them. First, the polar satellites. Polar or more appropriately near polar orbits have an inclination near 90 degree. So, satellites orbit in these orbits follow a circular path from pole to pole. So, they are capable of seeing each and every part of the Earth in a cycle of the satellite. It can be understood from the figure 3. These satellites are basically inserted into sun synchronous orbits which place the spacecraft in a relatively constant relationship to the sun. It enables the satellite to pass over a section of Earth at the same time, that is the local time of the place or the day. This satellite is very useful for predicting weather and also acts as a surveillance satellite. They orbit at an altitude of about 700 to 800 kilometers and takes about 100 minutes for these satellites to orbit the sun. And it takes about 100 minutes for these satellites to orbit the Earth. So they complete about 14 orbits in a day. Since the Earth is rotating beneath the satellite passes over a different longitude each time. It goes around the Earth, that is, the satellites see a new swath of the Earth on every orbit. Now, geosynchronous or geostationary satellites. These satellites orbit the Earth at the same rate as the Earth spins. So, its orbital period is equal to 1 sidereal day, that is 23 hours, 56 minutes and 4.09 seconds. Its orbit is at an altitude of about 36,000 kilometers above the Earth. In order to maintain a constant height and equilibrium, these satellites are located over the equator. This is because above the equator there is a constant force of gravity from all directions. These satellites are capable of viewing an entire hemisphere at a time. Most of the satellite images shown on Weather Channel are through these satellites. They are helpful in studying the extreme weather events like cyclones on a large scale. They are also used as communication satellites. Now, what is the difference between geosynchronous and geostationary satellites? Now, let us understand the difference between them. A geostationary satellite is having no eccentricity and has zero inclination. The orbital eccentricity of an astronomical object is a parameter that determines the amount by which its orbit around another body deviates from a perfect circle. Values between 0 and 1 form an elliptical orbit, 1 is a parabolic escape orbit and greater than 1 is a hyperbola. On the other hand, inclination of a satellite's orbit refers to the angle at which it crosses the equator. This enables the satellite to stay over the same point of Earth's equator as if it is stationary in the sky. When these satellites are given a small eccentricity and inclination, they become geosynchronous. So, to an observer on Earth, every day the satellite will appear in the orbit at the same place in the sky at the same time of the day. They make tiny figure 8s in the sky instead of staying stationary like geostationary satellites at a particular place. Communication and surveillance satellites basically make use of geosynchronous satellites which has a small eccentricity and inclination in order to ignore small perturbations of satellites due to natural causes. Due to this, ground antennae are able to see a comparatively larger area in the sky, so that if the satellite stays within that area, the communication is retained. Refer to figure 4 to understand the difference between geosynchronous and geostationary satellites. In this module so far, you have studied in brief about remote sensing, different types of weather satellites and its basics. Now let us study about satellite remote sensing for climatology, specially for weather forecasting. Satellite remote sensing is increasingly gaining importance in providing data for inaccessible regions in lesser time with the help of high resolution imageries. It provides climate variables with a large regional coverage, even up to the global coverage. Currently, land surface temperature maps can be prepared by combining a DTM digital terrain model with brightness temperatures derived from Meteosat. which is meteorological satellites. Thermal infrared challenge. With the help of these techniques, even evapotranspiration maps can be prepared. Apart from providing information about atmospheric combination, land use, land cover change can be done quite effectively with the help of satellite imageries. A change in land use and land cover can in turn bring change in different climatic variables like temperature, pressure, wind direction, amount of rainfall, etc. Now, satellite remote sensing for weather forecasting. You will study about weather forecasting in detail in module 39 of this course. However, let us get a brief introduction to satellite remote sensing and weather forecasting in this module also. You have already been introduced to satellite climatology, which received a wide recognition after the launch of the first meteorological satellite, TEROS-1, in 1960 by United States. With this, several developments took place like the use of radars, weather satellites, high configuration computers, statistical and computer models in weather forecasting, etc. We have already been acquainted with sun-synchronous and geosynchronous satellites. Some of the examples of geosynchronous meteorological satellites are GMS, which is the Geostationary Meteorological Satellite, FY2, FENUN2, GOMS, Geostationary Operational Meteorological Satellite, INSAT, Indian National Satellite System, INDO-X, Indian Ocean Experiment, Meteosat, which is the meteorological satellites, GOES-E, Geostationary Operational Environmental Satellite East, and GOES-W, which is the Geostationary Operational Environmental Satellite West, etc. On the other hand, examples of polar orbiting satellites are the NOAA, which is National Oceanic and Atmospheric Administration Series, FY1, FENUN1, FENUN2 series, TRMM, Tropical Rainfall Measuring Mission, Quick Scatterometer, etc. Thus, we see that apart from several weather instruments, climatic data and measurements are also taken with the help of satellites and its sensors. So, what is the difference between the data generated from conventional weather instruments and those from satellites? The answer to this is that conventional weather instruments like anemometers measuring wind, barometers measuring pressure, rain gauges which is for recording rainfall, etc., can only take measurements locally, that is for a very limited area, while satellites being placed at a distance are able to take measurements for a relatively larger area. GOES, which is the Geostationary Operational Environmental Satellites, because of their high altitudes are capable of recording the upper air meteorological data. Geostationary satellites provide continuous monitoring, while polar satellites views most of the earth twice in a 24-hour period, one during the daytime and one during darkness. The data provided by these satellites is relevant for study of weather system dynamics. In a way, a global system of space observation with both geostationary and polar orbiting satellites has evolved. NOAA is a polar satellite of low altitude and has various sensors meant to take different observations. Some of them are mentioned below along with their functions. The Earth Radiation Budget (ERB), it measures the energy budget of the atmosphere and Earth. Now, the Total Ozone Mapping Spectrometer (TOMS), it obtains data regarding the ozone, solar backscatter ultraviolet energy (SBUV). It monitors and evaluates the atmospheric ozone. Stratospheric and Mesospheric Sounder (SAMS), it records the temperature of the atmosphere. Now, GOES Imager, Geostationary operational environmental satellite imager. It records the solar radiation and energy reflected by the Earth's surface. Now, let us learn about the importance of GIS or Geographical Information System. Climatology and Geographical Information System. GIS has evolved as a powerful management tool for capturing, modeling, analysis and displaying of climatological data. In order to understand things better, first let us learn about the basics of GIS in brief. Basics of GIS. A Geographical Information System or GIS is a computer system for capturing, storing, querying, analyzing, retrieving and displaying the geospatial data. Components of GIS includes hardware, software, network, data, people and procedures. Geospatial data is also called geographically referenced data and describe both geographical location and attributes of different entities. The geographical location gives the coordinate information xy on a plane coordinate system or the information about longitude x and latitude y of any entity. Spatial information also relates to their geometry or shape, whereas attributes of the geospatial features includes their properties or characteristics which distinguishes one entity from the other. Refer to figure 5 to see different spatial or geometrical features as well as their attributes represented on respective tables. As a student of geography, you should know about projections. They are also important in GIS as we deal with maps. So projection is a process that transforms the Earth's spherical surface to a plane surface. However, it is true that this transformation leads to some distortion and there are also many plane coordinate systems that have been in use to preserve the spatial properties of the Earth to some extent. To align with one other spatially, different map layers must be based on the same coordinate system. You can refer to figure 6 to see how different layers are overlaid on one another because they happen to have the same coordinate system and projection and all layers are finally integrated at the end. Spatial data in GIS has two primary formats or models, that is the raster and vector data models. Vector data models uses points and their xy coordinates information to construct features like points, lines and polygons and appear very much like a map. Any thematic map is represented with the help of point, line and polygon features arranged in different layers on a map. Raster data model on one hand generalizes the scene into a grid of cells which each with a code to indicate the feature being depicted. The cell is the minimum mapping unit. Refer to figure 7 to get a clear picture of vector and raster data models. Let us now focus ourselves on the importance of GIS in climatology. GIS combines database technology with computer assisted cartography and it is very useful in representing climatological phenomena which are naturally spatial variables. It offers a useful platform for the representation and management of vast spatial data sets for a variety of applications. It provides a standard means of overlaying and combining data for analysis. Climatic data like occurrences of lightning strikes can be represented as points on a GIS map. Similarly, isolines like isotherms, isobars, etc. are represented as lines on the vector map. Also, digital terrain models or DTMs are used increasingly for extraction and extrapolation of climatic data, especially for high elevation mountainous environments. Raster DTMs are then simplified into TINs, triangulated irregular network, from which the microclimate of each triangle or facet is readily circulated via a variety of simple algorithms. Now let us get acquainted with the application of climatic datasets in several fields. These days, GIS has a very wide spectrum for its users. This helps in understanding the spatial, temporal and spatio-temporal variations in different components. Since they are numerous, only a few climatic or related branches are touched upon very briefly below. Now in agriculture and forestry, GIS has a great potential for agroclimatic modeling. A combination of maps containing different layers like soil, nutrients, water stress, fertility maps, etc. can predict the agricultural yield. With the help of temporal remote sensing data along with soil, rainfall and temperature data, growing index of a particular crop can be found out. It could also explore the possibility of finding out more suitable regions for growing of a particular crop. GIS can also be used to monitor biogenic emissions, agricultural pollution or water stress areas. Similarly, in forestry, GIS can enable us to find out suitable sites for afforestation. GIS can be used for delineating forest zones, mapping of forest paths, model the spread of forest fire, etc. GIS integrated with remote sensing techniques can also be used to monitor forest cover change over time and also model forest recovery. Now in ecology, GIS based agroclimatic models can be used to model ecological biodiversity with respect to spatial climatic data sets. With the help of GIS, the impact of various elements of climate on different series can be studied. In health and diseases, various vector-borne diseases have geographical indicators, especially those related to climate. These can be modified effectively using a GIS platform in order to control their spread and save the lives of people. Diseases like malaria, dengue, and many other are creating a lot of havoc these days, and their geographical indicators needs to be properly studied to find out their possible areas of outbreak so that proper safety measures can be taken in advance. We need to take the help of remote sensing and GIS. Now in hydrology, GIS plays a great role in hydrological field too. Hydrological parameters like spatial distribution of precipitation, forms and types of precipitation all have spatial expression which can be represented on a map. Amount of rainfall combined with DTM can also be modeled to give an idea about flood forecast. Satellite imageries and GIS maps can also help in the exploration of underground water and also study the change in groundwater levels. Now in urban environment and transport. We all know that urban environment is rapidly deteriorating due to vehicular traffic congestion and gaseous emissions. Due to industrialization, production of goods has increased to a great extent, but it has also taken a great toll of the ambient air quality of urban environment. Suspended particulate matter (SPM) is creating an atmospheric haze by obscuring the adequate sunlight, especially during the winter months, and leads to several respiratory or lungs diseases in human beings. It is creating adverse effects on other living organisms as well. GIS can act as an inventory of emissions and also model them and correlate them with traffic data. GPS, which is the Global Positioning System, can help in automobile navigation and can be used to monitor traffic in integration with GIS. Thus, GIS can be used to study the pollution and also help in climatic modeling studies. Remote sensing integrated with GIS can help in the study of urban heat islands, which is due to heavy concretization and construction of high-rise buildings in urban areas. Now in climate change studies, Climate change refers to any significant change in the measure of climate such as temperature, pressure or wind, precipitation lasting for an extended period, say a decade or longer. Due to human activities, Earth is becoming warmer. As per NASA's estimates, Earth's average surface temperature has increased to about 1.2 to 1.4 degree Fahrenheit since 1900. This increase in temperature is attributed to the excessive use of fossil fuels such as coal, petroleum, natural gas, etc., which has increased the levels of greenhouse gases in the atmosphere. These greenhouse gases are responsible for tremendous increase in the temperature of the Earth, as they trap the outgoing long-wave terrestrial radiation from escaping and thus produce a greenhouse effect by raising the temperature of the Earth. GIS has become a visualization tool for the output of climatic models such as general circulation models used to predict the global impacts of hypothesized climate change scenarios. Now, with the help of GIS, one can study the effect of climate change in agriculture and ecology. GIS can also study climate change implication on health of living organisms, land use, land cover change, effects of deforestation, desertification, urbanization, etc. Now, in disaster monitoring and management. In the recent years, GIS is used as a tool for management of disasters as it amalgamates geospatial data with socio-economic information for better decision making in handling any disaster. Various governmental agencies and decision makers are using GIS for better prediction, monitoring and lastly management of disasters. GIS combines various layers of information containing different themes that helps the policy makers in different levels of disaster management, that is in the pre-disaster planning, prediction and early warning of disasters and damage assessment and relief management. Through GIS maps, both vulnerable areas and comparatively safer areas for disasters can be identified. This would help in evacuating the population from vulnerable areas and rehabilitating them in the safer areas. This would also aid in smooth organization of post-disaster operations. Now, let us recapitulate what we have learned so far. Today, technological progress in climatology is attributed to the use of remote sensing and GIS in climatology and meteorology. Prior to the advent of satellite data and GIS technology, most of the climatic data was collected with the help of ground survey. Systematic collection and dissemination of weather related information started with the introduction of telegraph technology. With the advent of satellites, climatological data is obtained very easily. It covers a wider area that needs to be studied with fewer efforts. It is cheap, less time consuming and very precise in terms of accuracy. Basically, there are two types of weather satellites, namely the sun synchronous and the geosynchronous satellites. Satellite remote sensing is increasingly gaining importance in providing data for inaccessible regions of the Earth in lesser time with high resolution imageries. It can provide climatic variables with a large regional coverage, even up to global coverage. The geostationary satellites provides continuous monitoring, while polar satellites views most of the Earth twice in a 24-hour period, one during the daytime and one during the darkness. The data is relevant for the study of weather system dynamics. GIS is a computer-based system for storing, capturing, querying, analyzing, retrieving and displaying the geospatial data. GIS is an organized collection of hardware, software, network, data, people, procedures. Spatial data in GIS has two primary formats, that is the raster and the vector. GIS combines database technology with computer assisted cartography and is useful in representing climatological phenomena which are naturally spatial variables. Climatic data sets are used in several fields like agriculture, forestry, ecology, urban environment, health, climate change studies, disaster management, etc. Thank you very much.